Okay, so Zoom, set recording. This picture here is what we're going to be computing in today's lecture. Last time, what we did was we did our first honest to goodness renormalization group transformation. We did a real space renormalization. So we literally started off with a lattice of spins as shown in the middle of the page. Then we grouped them into blocks, which are the gray things, and then we integrated out the degrees of freedom, which are the vertices of those blocks. That gave us a single spin variable for each block, which I called SI, and I called the microscopic variables in each spin sigma I, just to save writing. And what we did was we integrated those out, and we derived a formula for the effective Hamiltonian on the larger lattice shown in the thick black triangle in the middle there, slightly rotated from the original lattice and with a size that is bigger by a factor of √3. And what we did was we did the cumulative expansion. So essentially what we're doing is in computing what you see on the left-hand side, the integrating out the microscopic degrees of freedom for the effective Hamiltonian. What we're essentially doing is computing the expectation value of the interactions between the block spins, which I called V. And so what we have to calculate is the expectation value of e to the V. And what we did was we used the cumulative expansion to do that. So the cumulative expansion basically was to write the expectation value of e to the V as a power series in V, and then resum that series, because we know that ultimately the expectation value of e to the V, we're going to want to read off the effective Hamiltonian, which comes in as e to the H. So we want to take the logarithm of that. And so when we take the logarithm of that, then what we find is that the expansion for the expectation value of e to the V is what is shown here in the middle of the left-hand panel. And it has this very important form like this, which you'll see over and over again in statistical mechanics, in quantum field theory, in statistics. And it's basically a way to resum terms of the series in a way that is beyond what you would do just by doing regular perturbation theory. So we just did this in a very ad hoc way because I only went to second order. But if I wanted to go to higher order, one can do that in a systematic way, and that's called the cumulative expansion. So what we did last time was we evaluated all the interactions between the microscopic spins on neighboring blocks. We did a calculation, and in the end, we derived what you can see on the left-hand side screen. We derived the effective Hamiltonian now in terms of just the block spin variables. And apart from some constants, m log z naught that we calculated, we saw that at least to this order in perturbation theory, it has the same form as the nearest neighbor Ising model that we started with, but with a new coupling constant. And that coupling constant is given down here on the left. The k prime is 2k 5k squared, where this function phi of k is calculated over here on the middle of the page. Okay, so now we have explicitly done what we set out to do, and then we just had to follow the program that we derived last week. So we looked at the fixed points, we found what they are. We then calculated the linearized renormalization group eigenvalues around those fixed points. We computed the eigenvalues lambda t shown over here. And then we compared what lambda t is to the exact value for the renormalization group eigenvalue that we obtained from Onsager's exact solution of the Ising model by working backwards from his calculation to compute what we should have got for the eigenvalue if we'd been able to do this exactly. And you can see that it is a reasonable agreement. So that's where we left things last time. So what I want to do is I want to go to higher order in the cumulative expansion. And I'm not going to do all the calculation. I'm going to show you how they're done. But the main things I want to show you is that we now generate new interactions when we go to higher order, and we get improved values for the critical exponents. So we're going to start off with that. I'm going to say a little bit about how to include the external magnetic field. So up to now, we set H equal to 0, but of course we can do this with H being non-zero. It just adds more complication. And so I just want to show you a very quick and dirty trick to get at least the lowest order calculation for the external field. And then we will look at the flow diagram that we've obtained. And I'll show you that the phases of the system are indeed the sinks of the renormalization group flow diagram. And lastly, I want to introduce to you the idea of the transfer matrix, which is something that you've seen in the homework in a kind of embryonic form. And I want to make that connection just a little bit more precise. Okay, so let's get to it. So I'm just going to jump straight in with computing the second order cumulative expansion. So what we have to calculate then is the next order term is v squared minus expectation value of v all squared. And if I write that out, that is a fairly complicated thing. So it looks like this. I'm going to write it out and I'm going to draw you a little picture so you can see where these terms come from. And so that's what I think, what I claim it is. Now, what does this mean? So I need to draw you this picture. So I'm going to now have to draw this block spin like this, and then the neighboring block spin looks like that. So this is the block spin Sj, this is the block spin Si, and then there are interactions between, since on the microscopic lattice, nearest neighbors are interacting, so I'm drawing in those. And the geometry here is that this might be, say, the spin Si, this might be the spin Sm, this might be the spin Sn, and this might be the spin Sj. And in order for these interactions to be non-zero, because we remember that the basic microscopic interactions are all nearest neighbor, then what I need is that I and j have to be on different blocks. And m and n have to be on different blocks. So why is it like that? Well, remember that our perturbation theory starts off by saying the zeroth order perturbation theory is just, we're looking at interactions within a block, and then the perturbation is the interactions between blocks. So when I write down V, that only included interactions between blocks. And so what I've drawn here are the interactions between spins on different blocks. So you can see spin M is interacting with spin N, and they're on different blocks. Spin I and spin J are on different blocks. So that's the constraint that I need. So I'm going to just go through this fairly quickly. Don't worry if you don't get it completely, but I just want to show you that the logic of this. Question, yeah.
I was wondering, I wasn't here for the last
yes.
one, but I watched it online. And something I was confused about is that, so Si and Sj, the microscopic spins, are not nearest neighbors, right? So it's our original.
Do you mean the microscopic ones?
The microscopic.
Yes.
So why would we consider their interaction if in the original model we only have
well, I'm about to actually try to explain that. Okay. So there won't. So the bottom line is there won't be an interaction. Okay. Let me just go and explain that. Yeah. So and then if I didn't answer the question, then ask it again. Okay. In like 2 minutes time. Okay. So now let's have a look at this Si Sj0. Okay, so that's like the term that you're asking about, for example. So this, because they are independent, remember that when I'm taking this angle bracket, it's just with respect to the Hamiltonian on the block spin that they are in. That's what the expectation of zero means. So this factorizes. So this is SI 0, Sj 0. And that, if they're on the same spin, that's going to be 0. So that will be 0 unless Si is in the same block as Sn, and Sj is in the same block as Sn. So when I write down these terms over here, they have to be well, actually, I've drawn them in the opposite way. So if m and n were as I've drawn them, that actually would be 0 in this picture here. But if Si is literally in the same block as Sn, then when I do this calculation, then I will get something that is non-zero. So I didn't explain that very well. I don't know how to explain it better though. I mean, the main point I want to make is that I and J definitely cannot be in the same block. So what I'm saying is, in order for this thing to not be 0, I have to effectively, after I've done this calculation, there will be an interaction that is generated effectively between spins that are second and third nearest neighbors. I don't know why I don't know how to explain it better than that. Probably did I explain it better in my book? I may. I don't. I can't explain it better. I'm going to just go on and then come back to it. Yeah, I'm going to ask that you read what I wrote in the book in my notes. I don't, because if you don't, read. I mean, I can't say it any better than. I mean, the point is this. This thing, what we're trying to answer is, if this thing just completely factorizes this expression I've written up here, then it will just be 0. Okay, so you have to ask, what are the ways that it could not be 0? And the only way that could happen would be, for example, so the expectation value of Si Sm. I mean, if you have this equation, then everything will factorize and everything will be 0. So what you have to have is that I is in the same block as M and J is in the same block as Sn, or the other way around. It doesn't matter. So I should say here or other way around. It doesn't really matter. And then this thing will not be zero. There'll be quadratic terms that don't cancel out. So the thing that I don't know. Yeah, I don't know how to say it more clearly than what I just said. The main thing is that I and M have to be in different blocks than N and J, or the other way around. And so when I'm looking at the interactions between spins, I'm not looking at what is the interaction in the Hamiltonian. I'm looking at what are the terms in this correlation function that are non-zero. The terms in the correlation function that are non-zero are ones that involve three spins that are in different different blocks, and therefore second and third spin interactions, effective second and third spin interactions. Okay, so I'm going to leave it. I'm going to leave it like that, and come back to this afterwards or privately. So what will happen? So the upshot of this is that you end up with the second and third nearest neighbor block spin interactions. So in other words, what I'm showing you is that remember, what are interactions in the Hamiltonian are correlations between the microscopic degrees of freedom, and that's the thing that's confusing about this. Okay, so I'm going to go on, and because I've got a lot of other things I want to get to in the lecture, and I don't want to focus on how to do the calculation. Okay, now let me just tell you what the results are. Okay, so the first thing is that this time I get that lambda t, the thermal eigenvalue, is 1.77. But now I've generated a lambda 2 and a lambda 3. So these are eigenvalues that correspond to second and third nearest neighbor interactions. So this is second nearest neighbor, and this is third nearest neighbor. And what I want you to see is that this one is 0.23, and this one turns out to be minus 0.12. Okay, now why did I show you those? So the point is that the magnitude of these eigenvalues is less than 1. And so these are irrelevant variables. So they're irrelevant variables. So they're irrelevant, but these couplings are generated by RG in order to get an accurate estimate of the relevant eigenvalue. So let me just remind you what those were. So the exact value for lambda from Onsager is the square root of 3, which is 1.73, something or other. At the first order in perturbation theory, I got 1.62, and at the second order in perturbation theory, I got 1.77. So you can see that I'm getting improved accuracy, but at the expense of having to consider these other second and third nearest neighbor interactions. So I can't just look at just nearest neighbor interactions. That's the point. So that's the that's why we have to do that. Okay, so next thing I want to talk about is how do we compute the magnetic field eigenvalue. So next thing we want is the magnetic field eigenvalue. And so we're now going to set H to be non-zero, and then we want to compute lambda H. And the way I'm going to do this is I'm going to do this using a trick. And so, but you can do this precisely as well. Actually, in the homework, I do have a homework problem that I didn't give you yet, but I may add it to the homework that I will send out later today. A short homework with many optional questions. So here is the trick. So we know that the critical field value is equal to 0. So what that means is that if I want to compute the delta H, which is my change in my coupling constant H, we can ask how does it affect the calculation of the effective Hamiltonian. And so let's look at that. So the way we defined our effective Hamiltonian is like so. So it's e to the h prime, then it's the sum over the microscopic degrees of freedom, sigma I. Now it's e to the h, which is what we did last time, but now I've got a perturbation added onto this. So that perturbation I'm writing as delta h. Actually, let me write this as delta h prime, like so. And the perturbation is delta h is h sum over I si, which is the same thing as delta h sum over I si. So that's the coupling to the external magnetic field, and so I can write that as the change in magnetic field, and then the sum over all the spins. This is the sum over all the spins, so I can write that as the sum over the blocks, and then the sum over the spins inside the block, like so. So that is the perturbation that I've added to the calculation I did last time by including an external magnetic field. So why is this useful? So I can then read off that that delta H prime is then just delta H prime the original field times the sum over I of Si. So that's the perturbation to the renormalized effective Hamiltonian, and so I can write that as the sum over the spins of e to the h times delta h divided by the sum over the spins of e to the h. So when I want to compute the expectation value of this object, what I have to compute is the things I've written over here. So I know what that is. Now, the reason this is simple is the following. So if I compute delta H prime as the expectation value of delta H, sum over I in I Si, like so. So I can write this as delta H, then the sum over I of S1I plus S2I plus S3I. Okay, so that's already that's just the sum over the spins in that block. The point about this thing, oh, I want to put an expectation value around it. Okay, the thing about it is this thing we already computed. Why did we already compute it? Well, when we were integrating out the spins to order to the first order, we actually computed what this sum is, and that's basically over here. That's basically what I'm showing you on this page. So I already know that this thing is equal to, bless you, this thing I can get from saying this is SI is just SI times this function 5k, and this is true for every I equals 1, 2, or 3. And so I can then read off that delta H prime is 3 phi of k times delta H. So the point is, without doing any new calculation, I can read off what is the renormalization group recursion relation for the change in the magnetic field. Okay, so what does that give me? So now that I've done that, then I can simply calculate what lambda H is. So that is then I've got to differentiate delta H prime and set it equal to H star. So that is then 3 phi at the critical point Kc, and phi of Kc we already calculated was 1 over the square root of 2. So this is 3 over the square root of 2, which is 2.12. Okay, so that's the renormalization group calculation to 0th order in V without doing any extra calculation. So, so if we compare this with Onsager's calculation, so the Onsager calculation gave you 2.8, and so again it is reasonable. And I'm not going to go through and do the calculation to higher order, but that can be done. Okay, so now I want to look at the phase diagram. So let me copy the phase diagram over to this page. Here. Okay, so this is the renormalization group flow diagram, and I want to calculate what the behavior of this is. So let me see where I got this from. So how do I know this? So we know this because if we look along the H equals 0 axis, we've got the k-axis on the horizontal, the h-axis on the vertical. So what do I have? I have a critical fixed point, which is the one that we just calculated last time, and we can calculate our estimate for the critical temperature. What we've seen is that it has unstable directions because lambda t is positive. So this critical fixed point is unstable. And then I'm going to show you that there's another fixed point, the paramagnetic fixed point. And that one is a stable fixed point. And then there is a ferromagnetic fixed point, F. And that one is also stable. So the values of these fixed points, they're on H equals 0, and as you can see, the way I've drawn it is that the h equals 0 axis, this thing is the invariant manifold. You stay on h equals 0, you stay on the h equals 0 manifold. If, on the other hand, you're slightly up in the h direction, then you flow away to these other fixed points at plus or minus infinity. Okay, so the only stable fixed points are the ones at h equals 0 and k equals 0 or infinity. So let's write that down, that you can see from this flow that h non-zero, that implies that you then flow to plus or minus infinity for the h values. Okay, so now let me so this is what the flow diagram looks like. Let's calculate what the eigenvalues are at these different fixed points. So let's have a look at the paramagnetic fixed point. So at the paramagnetic fixed point, you can calculate the linearized eigenvalue transformations. So I simply have to look at the renormalization group transformations that we derived last time, and I'm not going to go ahead and do that. So what you find is that if I'm evaluating at the paramagnetic fixed point, so then so again, all I'm doing to do this is I'm calculating, going back to this calculation, one we did last time, over here. So here is our RG transformation. So I'm going to, so the fixed points for this were either 0, infinity, or k star. So these are the fixed points. And so what I'm going to do now is, last time we evaluated the transformation by linearizing around k star, but now what happened if we look at the paramagnetic fixed point? So then what you get is that lambda t is 1/2, and it turns out that lambda h is equal to 3/2. So this then is a stable fixed point, as I told you. If I look at the ferromagnetic fixed point, so the ferromagnetic fixed point, that's the one over here on the left, where k has gone to infinity. So now I evaluate the linearized RG of that transformation around k equals infinity. And if you go ahead and do that, what you find is lambda t is equal to 2, and lambda h is equal to 3. So again, all I'm doing is taking the same RG recursion relation that we derived last time, and just evaluating the derivatives dk by dk, and then calculating the h exponent of about these different fixed points of this fixed point equation. Okay, so everybody happy about how I got those results, even though I didn't show you the actual algebra? Yep. Okay. You can do that in the homework, just to go back and check that. Okay. So now there's a question that you should be asking. So you might say, wait, f is supposedly a stable fixed point. I've drawn the flow as it's going away from the critical fixed point. It's got nowhere else to go except the critical fixed point, except the ferromagnetic fixed point is infinity. If it was a stable fixed point, then you would expect lambda t was actually less than 1. but it's not, it's 2. So what's going on? So the answer to this is an artifact of being at infinity. So it's kind of weird when you're at infinity. So what you should do is write the RG recursion relation in terms of 1 over k, so k to the minus 1. So then you get k to the minus 1 prime is 1/2 k minus 1. And so then you can see that k minus 1 equals 0 is attractive. And so in other words, k prime is greater than k, but that's still an attractive fixed point if you're going to infinity. So don't worry about that, because you can't really linearize about a point at infinity. You have to linearize about a point, an inverse point at 0. Okay, so that's the first comment. There's a second comment I want to make, which is much more important. So that's comment number 1. Comment number 2. Comment number 2 is, if you look at lambda h at the ferromagnetic fixed point, that has the value equal to 3. Okay, now you might say, okay, so what, who cares? Okay, well, this has special significance because I'll tell you why. I'm not going to go through again why it is like this, but remember that our L is equal to the square root of 3. The way that we did our block spin transformation, the system L has gone up by a factor of root 3. So that means that when I write down lambda h is equal to 3, that is in fact root 3 squared. And so lambda h in this particular case is equal to L to the d, where L is equal to root 3 and d is equal to 2. And what you can show, and it's in my book, but I'm not going to go through it. Whenever you have such an exponent, this indicates a discontinuity in the way that m varies in the h direction. And we know that's true because remember what our phase diagram is. Our phase diagram looks something like this. So here is temperature, here is h, and then there's a discontinuity along here. Here is Tc, and then we know that in this direction we have a second order phase transition, a continuous phase transition, and in this direction, here the spins are up, here the spins are down, and so m changes continuously for t less than Tc as you go from h is 0 minus to 0 plus. And you can see that this first order transition is that there is an eigenvalue whose value is L to the D. And that's in section 9.7 in the book, but I'm not going to spend any more time on that. So this simple calculation that we've done here is already telling us an important amount of information about the system that we otherwise would not have known. Okay, so I think that's all I want to say about the flow diagram for this case. I think what I want to do now is talk a little bit about the transfer matrix, which is a somewhat different topic, but it's related, and in what I'm going to do is give you as homework today is basically one of the optional questions from the last homework sheet, which was to do the renormalization group calculation and compare with the transfer matrix. So I want to give you just a little bit of understanding of what the transfer matrix is, because it's another way to think about what you're doing in the normalization group terms. So it's not very complicated. In fact, it's amazingly simple, but amazingly powerful. So, so what is my goal in this section? I want to show you a way to think about statistical mechanics. In a different formalism. And what it does is it's a generalization of the homework that you did, where I asked you to generate recursion relations between correlation functions and spin values at different points in space. So let me get into it, and you'll see the connection. Okay, so the starting point is the partition function, which I'm going to write like this. And I've got n spins, and so this is just the trace of e to the h sum of I si plus k I si si plus 1. So what I'm doing here is I'm looking in one dimension, and I've got a bunch of spins on these lattice sites. This, so here's spin 1, spin 2, all the way up to spin n, and then I've got periodic boundary conditions. So you can imagine that as meaning that there is a phantom spin here, Sn plus 1, but that spin is actually identical to spin S1. So that's what I mean by periodic boundary conditions. And so writing the problem this way, even the d equals 1 Ising model is hard, because the partition function is not equal to z1 raised to the nth power. That's the thing that enables us to solve any problem, is if we can factorize the partition function, then we can do it. That's what happens with say the power magnet. And the reason we can't do that is because of this interaction term over here. So that's the thing that messes everything up. So the transfer matrix is a trick to actually figure out how to factorize it. So what the transfer matrix is a way to kind of, I'm going to put just brackets, parentheses around this, is a way to factorize the partition function. It's very clever, and the idea is as follows. So here's the trick. I write down my partition function in this way. first of all, I've got a sum over all the spin variables, S1 up to spin n. Okay, so that's what I have to do. And now what I'm going to do is I'm going to write this Hamiltonian in a very sneaky form. So I'm going to write it like this: e to the h over 2 S1 plus S2 plus k S1 S2. So that's the first term. Then the second term, I'm going to write this as e to the h over 2 S2 plus S3 plus k S2 S3 times dot, dot, dot. And then when I get to the end, what do I have? I have e to the h over 2 spin n, and then spin n plus 1 is really spin 1. So it goes like that, plus k Sn S1. Okay, so let's have a quick look at this. So what I want you to notice is that, first of all, the first term is h over 2 S1. The second term is e to the h over 2 S2. Okay, so you say, well, we've got the wrong field value. But if you look at the next term, in the next square bracket, over here, I have e to the h over 2 S2. That adds to the h over 2 S2 from the first bracket. And so that gives me the e to the h times S2. The k's are all fine. And then the last one is Sn plus S1, because it's periodic boundary conditions, that gives me the extra factor. So this thing is exactly, without any approximation, equal to my original partition function. Okay, so now that's just the first thing. It's a clever way to rewrite it. The next thing is, so that's step one. Rewrite. Okay, step two is interpret these square brackets as matrices. So I'm going to write down what the matrix is, and then show you that it actually it really is a matrix. So I'm going to define an operator T S1 S2 is equal to e to the h over 2 S1 plus S2 plus k S1 S2. So that's just a definition. And I claim that this thing is like a matrix element. So I'm thinking of this, of the S1 and S2 as being labels for the elements of a matrix. So S1 can be plus or minus 1, S2 can be plus or minus 1, and so that generates four numbers, T11, T1 minus 1, T minus 1, 1, and T minus 1, minus 1. And I'm going to put those things into a matrix like this, and this thing is my transfer matrix. So that's how I'm defining it. Okay, so the S1 and S2, even though those are spin variables and having the values plus or minus 1, you can think of those as being like the labels I and J of a matrix. Okay, so that's what those things are. And I can write down what those numbers are because I can read them off. So if I put over here, now looking on the left-hand side, what happens when S1 is 1, S2 is 1, then I just substitute that into there, I get e to the h plus k. So I can write down this matrix T just by substituting in those numbers. So it looks like this, e to the h plus k, and then e to the minus k, when one is 1 and one is minus 1, they cancel out. And then e to the minus k, and then e to the minus h plus k. Okay, so this is a matrix, and you could say, well, I define this matrix, who cares? What's so good about this matrix? Well, here's the thing, here's the trick now. This is the clever part. If we were to write down, well then, what Zn is, so I claim it looks like this. It's the sum over S1, S2, dot, 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 all the way up to Sn. Okay, so I'm summing over those things. The first term over here, look on the left-hand side, this first term is just T S1, S2. T S1, S2. The third term, so the second term is T S2, S3. The third term is T S3, S4. And I keep on going. And then the last term is T Sn, S1. Okay. So do you see that those are the matrix terms? Now, what are we doing here? Well, the first thing we're doing is we're summing over S2. So we're summing over this, S2 comes here, and S2 comes over here. Okay, so let's have a look at what that means. The sum over the variable S2, T S1, T S2, T S2, S3, we're summing over S2, so this thing is like the rule of matrix multiplication. So if I have a matrix A is equal to the matrix B times C, then the way I would write that in component notation is Aij is the sum over K, B, I, K, C, K, J. So in other words, to get the ijth element of the matrix Aij, what I do is I sum over K here, I sum over this K, and this K, that's the dummy variable, and that gives me the matrix element Aij. So what you can see over here is the term that I've written in green. This is exactly the same thing. I'm summing over S2. There it is. There it is. And so this object is then, you can see what it is. What is it? Anybody tell me what that thing actually is? This thing over here. Right, this thing is just T squared. So the thing that I've drawn over there is T times T, and then which element is it? Somebody else. Somebody other than Connor. S1, S3. Okay, just like over here, when I do that, I get Aij. So here, this is the matrix S1, S3. All right. So now if I keep doing this, what I get is that Zn of H and K is equal to, so far I didn't do, I left out the sum of S1. So I've got T times T S1, S3, and then T times T S1, S3 times T S3, S4. So I've got T and so on and so forth. And so how many of those do I have? So I've got T S1, S2, T S2, S3, all the way up to T Sn, S1. And each of these variables inside here that I've circled, they've all been summed over with S2, S3, all the way up to Sn, and the only one that is left is S1. So this thing is then equal to the sum over the variable S1. And how many factors of t are there? 1, 2, all the way up to n. So I've got t, the matrix T to the n, and then what are its elements? So this is the matrix T to the n. What are its indices? Somebody else? S1 is 1, exactly. S1 is 1. And what is that? So that is the sum over the diagonal elements of the matrix. So that is then just trace of the matrix T to the n, because trace just means it just means like that. Okay, so this sounds okay, very nice. I've got a 2 by 2 matrix, and then the bad news is I've got to raise it to the nth power. Okay, so that's awful, but we can do a trick. Okay, so this looks awful, but isn't. This is now, what step am I on? Step 3. So what I can do is remember that the matrix I can diagonalize because the matrix T is symmetric. It's symmetric because of the structure of the original Hamiltonian. So how do you diagonalize a 2 by 2 symmetric matrix? So what you do is you simply just do this. You say, I'm going to make a transformation T prime. So what is this matrix? It's S to the minus 1 T times S, where S is the matrix of eigenvectors, and S transpose is equal to S to the minus 1. So this is just very basic linear algebra. And so what that means is that the matrix T prime, after doing that, is going to look like this: lambda naught, naught, lambda 2. So after diagonalization, it's going to have this structure. Okay. So lambda 1 and lambda 2 are eigenvalues of a 2 by 2 matrix. Okay. Now the great thing about the trace, if I have the matrix T and I have the matrix T prime, they have the same trace. The trace is invariant under this rotation by the eigenvectors, and you can easily prove that. So what that means is that if I were then to work out what is the trace of the matrix T to the n, this is just the same as the trace of the matrix T prime to the n. And the matrix T prime, since it's diagonal, when I multiply it to the nth power, it just has elements lambda 1 to the n, lambda 2 to the n. So this is the trace of lambda 1 to the n, 0, 0, lambda 2 to the n. Okay. So then that means that the partition function is just lambda 1 to the n plus lambda 2 to the n. Okay. And one of those eigenvalues, let's suppose that one is bigger than the other. Then I can write that the z to the n is equal to lambda 1 to the n times 1 plus lambda 2 over lambda 1 to the nth power. And now I take the thermodynamic limit, so I go to the nth, n going to infinity. So then that means that Zn of h and k is equal to lambda 1 to the nth plus 1 plus e to the n times the log of lambda 2 over lambda 1, which is very small. And so then I read off that that the bulk free energy per spin is the limit as n goes to infinity, the free energy h k t over n, and that is just going to be minus kbt times the log of lambda 1. So all I've got to do in the end is I've just got to compute the eigenvalue of a 2 by 2 matrix. So we can all do that, even full professors can do it. So step 4 is compute the eigenvalues. T. So what I need then is to solve the equation determinant of e to the h plus k minus lambda, e to the minus k, e to the minus k, e to the minus h plus k minus lambda. So that is equal to 0. And so then I can compute the two eigenvalues. I'll call them lambda 1 and lambda 2. And they go as e to the k times cosh k plus or minus square root of sine squared h plus e to the minus 4k, like so. And so that means then that the largest eigenvalue over n gives me the free energy, so that's minus kbt times then the logarithm of all of this with a plus sign, and noting that when I write down k was originally j over kbt, so I can then read off that fn over n is equal to minus j minus kbt times the logarithm of cosh h plus that square root, which I'm not going to write out, like so. And the square root is this thing over here. And this is exact. We've just solved the 1D Ising model exactly. Isn't that amazing? And Onzag, I figured out how to extend this to 2 dimensions. Okay, and it's completely non-trivial in 2 dimensions. Okay, now let's have a look at what this means. So the first question you might say is, well, I've got this formula here, doesn't look much like a phase transition. So how do I get phase transitions? So the first question that you can ask is can you get a phase transition this way? So the answer is no. If t is greater than 0, then that means that the square root is always positive. The argument of the square root is positive. So I can compute that as long as h and k are real. So they are. So inside the square root is some function, sine squared h plus e to the minus 4k. Nothing wrong about that. Add them up, get positive numbers, take the square root, nothing weird there. And so then I get that the bulk free energy per unit volume is then going to be some analytic function. And so that means that there's no phase transition. So one-dimensional Ising, there's no phase transition or non-zero temperature. And we saw that before. Remember we did the ergodicity breaking, and we saw there was something really weird about the ergodicity breaking in one dimension. Because remember that the ergodicity time went as e to the n to the d minus 1 over d. And I said at that point, as n goes to infinity and d is greater than 1, that thing diverges, and so you can get ergodicity breaking and spontaneous symmetry breaking. But in d equals 1, it doesn't, it stays finite. So we already had our intimation that 1d, there is no phase transition. And that's true. There isn't a phase transition for t greater than 0. Okay. Okay, so question 2. Is there a phase transition in d equals 1 at t equals 0? The answer is yes. So let's see. Let's just see why. So here's our lambda 1. So it looks like this: e to the k times cosh k plus the square root. I'm going to write it out now. Sine squared h plus e to the minus 4k. So that's our exact result. But as t goes to 0, this k is going to infinity. K is the coupling constant j over kt. So basically, this term, the e to the minus 4k, is negligible. And so then I say, well, then lambda 1 is equal to e to the k, and then cosh of k plus, cosh of h, excuse me. Cosh of h, and then the square root of sine squared h. What's the square root of sine squared h? Sine h. Okay, right? Except it's not. It's not. What is the square root of sine squared h? Yes, yes, exactly. No, so the correct answer is lambda 1 is e to the k times cosh h plus the absolute value of sine h. Okay, so just remember the square root of x squared is equal to the absolute value of x. Okay, so now let's have a look at what this is. So if I look at this, what is cosh h? What is cosh x plus the absolute value of sine x? So that is equal to e to the x plus e to the minus x, all of that. So what is that equal to? You look at the two cases, it's actually e to the absolute value of x. So that says that actually lambda 1 is e to the k plus the absolute value of H. Okay, so now I've got to compute the free energy. So then the free energy per spin is equal to minus n kBt times the logarithm of the lambda 1. So I get k plus the absolute value of h, like so. And remember, k is equal to j over kBt. So the reason I kept this k in there is because now it cancels out. So I get minus n times j plus the absolute value of h at t equals 0. So I kept the k in there because like the t cancels, so I can take the t goes to 0 limit. And so now I've got this function. This is the free energy. And you can see that it's non-analytic. It's non-analytic because this term here is non-analytic. So let's just check that. So we're at t equals 0, and it's going to be non-analytic where, while the function absolute value of h, mod h, is non-analytic at h equals 0. So let's compute the magnetization. So that's minus 1 over n df by dh. And you can see from this formula, just doing the differentiation, there's only h to 1 power. So I get 1 when h is greater than 0 and minus 1 when h is less than 0. And so we have a discontinuity. And thus a first order transition at h equals 0. And remember, we're still at t equals 0. So the phase diagram looks like this. So here is t, here is h. And then what we've just discovered is that what this phase diagram really looks like is that there is a phase transition right there. Okay, and that phase transition is a discontinuity in this direction. And what happens in this direction? Well, in this direction, well, you can't go back here to negative temperature. So this is some weird, kind of weird singular point, because something is happening as at h equals 0 and t going to 0, the lambda is going as e to the j over kt. So there's an essential singularity at t equals 0. So this is d equals 1. Okay, now compare this with d equals 2. So the only thing that's different about this in d equals 2 is that this point that was here has now moved up to here. And now, again, we still have this discontinuity through here, but now I also have this, I can now go below the critical temperature, and that is the second order transition. So going towards t equals 0, this is going as e to the j over kBt. So it's not a power law divergence. It's some kind of essential singularity. So that's what's happening at 0 temperature. Okay, so let's see, have I got everything I wanted to do? So I think that's it. Okay, so in general, I'm not going to say too much about this, but you may wonder how can you possibly ever get phase transitions at all in this formalism? So let me make a couple of comments about that. So the next question, I just want to make a couple of remarks and refer you to the book for more details. So given this whole picture of the transfer matrix with these eigenvalues, then the question is, how do you see phase transitions? In the transfer matrix picture. So there's basically three ways. So I could have that lambda 1 could be non-analytic. In H and K, that'd be one thing that could happen. I could have that lambda 1 equals lambda 2, and so that the square root thing is equal to 0, or I could have 3, that lambda 1 is equal to 0. Now, what we saw is that for t greater than 0 and d equals 1, none of these things happened. And so we know there's no phase transition. But there's a theorem called the Perron-Frobenius theorem. Perron-Frobenius theorem, which I'm not going to prove. And it says, take an n by n matrix. N is less than infinity. So let's call it A. And let it have positive definite matrix elements, Aij, for all I and j. Then we can prove that the eigenvalue of largest magnitude is A, real and positive, B, non-degenerate, and C, analytic. Aij. So in our case, our transfer matrix T is 2 by 2 matrix. And so that then implies that it satisfies the Perron-Frobenius theorem. And so that implies that there's no phase transitions because none of these things can happen. So the Perron-Frobenius theorem already tells us on general grounds why we can't have a phase transition at a non-zero temperature in the 1D Ising model. Okay. Now, we know there's a phase transition in the 2D Ising model because Onsager is super famous for figuring that out. So now the question is, how do you get a phase transition in the t equals 2 Ising model? So doesn't the Perron-Frobenius theorem, wouldn't it apply in 2 dimensions as well? How come we don't get a phase transition in 1 dimension, but we do get one in 2, and we have this general theorem, the Perron-Frobenius theorem, which basically looks like it stops you being able to have a phase transition. So how do we get round the Perron-Frobenius theorem? So look carefully at the statement of the Perron-Frobenius theorem. The AIJs are positive. Okay. But Connor was saying something. What were you saying, Connor?
I was saying something about that it requires, that's for n is a finite matrix, and maybe when you're doing it in 2D, you have to trace out over some strange pattern.
Right. Right. So So that's right. So in 2D, it's not obvious. To construct the transfer matrix, you have to take rows and then transfer rows, not just sort of single spins. And you can do that. It's a homework problem I'll give you where you can do this if you have time to do this. And then, of course, we have to take the thermodynamic limit. We take the n goes to infinity limit. In 1D, when you take the n goes to infinity limit, your transfer matrix still is just a 2x2 matrix. But in 2D, it's not. So the answer is that it becomes, T becomes a infinity by infinity matrix. And so that means that the Perron-Frobenius theorem doesn't apply. And so that's the mechanism. So in fact, what Onsager did was he showed how you can get this matrix and then you can map it on essentially to the quantum mechanics of ideal fermions and in space-time. And that way he was able to compute what happens and show that there's a phase transition. Okay, it's absolutely fantastic. And if you want to learn about it, which I do recommend for those of you who want to be theoretical physicists eventually, you want to look at a wonderful paper by Lieb, Mattis, and Schultz. And it's in Reviews of Modern Physics. And I'm doing this from memory. I don't have the notes in front of me. I think it's 1964. And this will be your guide to figure out how to do what Onsager did. You can read Onsager's original paper, and unless you're a genius, it'll just go, it's like listening to Doctor Who. Okay, but you read Lieb, Schultz, and it simplifies it, and you can a normal person can understand what happened. Okay, that's where I'm going to finish today's lecture. So next week we're going to do field theory renormalization group. So we are going to be looking at how to write functional integrals, field theory, and understand how you get anomalous dimensions and see where that comes from. We're not going to spend a lot of time on Feynman diagram calculations, but we're just going to have at least understand the basis of the formalism. Okay, so that's where we'll finish for today. So I'm going to stop the recording, and while I'm clearing up, I can take any questions. So let me just turn off the recording.